Okay, thank you. So it's Friday afternoon. Everybody are looking forward to weekend. So what's the plan today? I would say is half an hour reality plus half an hour daydreaming and 1/4 a mixture of this. So this is hopefully correct. So what is the reality part? We begin by review of the 3 talks. Okay. So recalling the first talk, our purpose is try to characterize locally symmetric space or symmetric space using global quantities. So one quantity is the volume entropy, the growth of the volume. And we can find the other quantity, which is a weaker form of this V, which is the mean curvature of the horosphere. It also has a dynamic meaning as the contraction ratio of the volume if we restrict the volume to the stable direction. Okay. So basically, 2 quantities, first lecture. And how about the second one? Second one, because this V in the negative curvature case is logical entropy, so we can try to interpret the relationship between this V and with the integral of V with respect to any geodesic flow invariant measure. That's the second talk. And among these measures, there are natural important candidates, maximum entropy measure and also Liouville measure. So we want to try to understand these measures. So in the second talk, we try to understand measures by lift this measure to the universal cover against the boundary. And we visualize it. One important class is the Patterson-Sullivan measure. That's the second talk. How about the third one? Third one, we start from this Patterson-Sullivan measure and we construct 2 classes of measures. One is the geodesic flow in maximum entropy measure called Bowen-Margulis measure. But there's also another class of measure which can be constructed using the Patterson-Sullivan measure is Rablin, right? So what's the relationship between V and this measure? Actually, you can see you have the equality, okay? And we didn't stop there because this Patterson-Sullivan measure is so useful. Actually, we start from this Patterson-Sullivan measure and do a little journey using what? Because this Patterson-Sullivan measure, if you consider this from the diffusion point of view, actually it corresponds to a diffusion with constant Martin kernel. This one corresponds to the Laplacian plus V x bar. Okay? So the class of measure we want to consider, a little change, is plus rho x bar, for rho is smaller than V, right? And for this class of harmonic measure, what does that mean? Means for any smooth function on Sm, actually you take the integral with respect to this m rho, unique harmonic function. Oh, I'm sorry. Here you have the operator, right? Okay, so you apply to Laplacian S plus rho x, apply to this function and take the integral, it should be 0. That's the meaning of Laplacian S plus rho x harmonic. Okay, so what is this new x rho? It's essentially a little change of the Patterson-Sullivan measure, and you combine it with the information from diffusion. So what is this d nu x? Of course, your action on this will satisfy beta and nu x rho. And the second thing is that I want to put it here is that if you change the base point, the Radon-Nikodym derivative will be similar to the Poisson-Sullivan measure is e to the power minus rho, and here you have the Boltzmann function, and times the Martin kernel for this operator, for the diffusion corresponding to this operator. This is x c rho. Okay, and evaluate that one. So here is, so I just put in this one. Boltzmann function, okay, here you have one, right? And here you also have one. Correct? Right? This is what we get. And so the measure m rho here actually satisfies is just, locally is just d nu x rho and d volume. Okay. So I will show you later. Actually, when rho equals to v, this one is constant. When rho equals to 0, rho equals to v, this one is constant. Rho equals to 0. Actually, what is this harmonic measure? It's exactly you consider the and this rho x is just the heating probability at the infinity boundary. Okay. So then, as you guess, once we introduced this kind of measure, so a natural question or the object we want to consider is the integral of this b with respect to dm rho. Okay? So now the question is, what is the special feature of this guy and how it's related to the dynamics? Okay? So we begin with this, and the first thing is to look at the dynamics. For this relative. Okay? There is obvious dynamics, is what we mentioned. So each unstable leaf can be identified with this m tutor times c. So on each leaf, actually, you have the diffusion, okay, to the boundary. And the diffusion, the heat kernel of this one will satisfy this. Let me just put simply this. Okay, this is the heat kernel. Okay, and now once you have these diffusions on the universal cover, actually we can do what Peter did in his talk to introduce dynamic quantities. What are those quantities? Actually, first, you can see you can define linear drift. Linear drift. So what is linear drift here? Actually, is speed of this diffusion on average. This L rho is actually, you can prove that with this probability and leafwise transition probability, actually you can calculate this one, the average of this D. You start from any x and you consider reference point doesn't matter, and you start from this. You consider the not-Brownian motion, the diffusion corresponding with this infinitesimal generator. This is omega t and t position, and you measure the distance, you take the average. So, but everything actually, when you consider the ergodic theory is downstairs. So you are using these kind of subadditive properties of this distance, you can show that for almost all orbits, actually this limit exists. Okay, but since we are on manifold, actually we can say more about this guy. So what is this limit? What is this limit? Now you are, remember that now you are on the leaf, on each leaf you have this diffusion. So if you start from x and on the leaf of this C, that means you are in the stable leaf of Ws of V, right? Okay, now you have a diffusion, and suppose for this orbit you will go to hit the infinity at C. So you see actually, because this t will, when rho is same, actually you have to go to a bound. And now what is this distance? Actually you see that you can replace this one by bx cos c by the Boltzmann. Why? Because the distance, what's the Boltzmann function? Now it's this one. It's this distance minus, here you let this point go to z, and you measure the difference of these two. So then what's the difference of this value with respect to the distance between x and omega t? Actually, as this omega t goes to cos c, this distance will be this difference will be bounded by the distance, in some sense, the Gromov product, something, right? And then actually bounded by this. So you can replace this by Boltzmann function. Then once you can replace this by Boltzmann function, you can do calculus. Okay? So intuitively, what is that? This is not very, this is not a proof, okay? So actually you do calculus, this is 0 to t, the differential of this with respect to time t. Time s ds. That is this. Because this is a diffusion, so the infinitesimal generator is Laplacian plus rho x. So the calculation here should be actually you can replace that by some martingale part, right? And then plus this one. This I mean you can replace this when you take the aspiratation. Actually, what is that? This part is Laplacian s plus rho x. You apply to Boltzmann function. So then what is this? Laplacian Boltzmann function is the function that we mentioned is b. And what is this? Rho x applied to Boltzmann function. Boltzmann function, the gradient is in the direction of x. So this is minus rho, right? So what does that mean? This means this linear drift is just, what did I say? I mean, here is minus rho, right? Is minus rho plus the integral of b dm rho. Okay? We keep this. We keep this. So you see, what? You see that's what I said. This Paxson-Sullivan measure, in some sense, can be seen as from the diffusion sense, is a kind of diffusion with a constant Martin kernel. Why? You have V here, and this guy equals to V. Minus V plus this, no change. No, there's no shift. What? Yeah. Okay. So this is L rho, the linear drift. So there's another quantity. We also have the entropy, stochastic. We also have this. Yeah. So what is that? It's similar to the random walk case. So here H, I have this notation, this H rho. Let me put it this way. H rho, actually, you also measure the decay rate. Logarithm of the heat kernel, not heat kernel, I mean the diffusion kernel. Okay, so this is the stochastic entropy. Actually, it's a same. You have to do something more here because this, in this continuous case, actually this guy is not subadditive. It's not that straight, but you have to do something to show this exists. You can replace this one by the decay rate of Green function. Okay. So you see, we can also obtain a formula here for H rho. The trick is that in the spirit of the same of L rho, you have the same calculations. But the point is that I want to point out is that we are in the non-symmetric case. So actually when you move, remember in the random walk case, actually you can replace this by a symmetric case, you replace this by the Martin kernel. But in the non-symmetric case, actually you need to replace this by the dual or something similar to the Martin kernel. You need to add something here, okay? So finally, the same computation. I won't do computations today. So here, hopefully, so what is the formula for H rho? Actually, H rho, we are satisfying this equation. Formula, I will put it here, is the gradient of logarithm of this Martin kernel. Actually, I will give a name for this density. This is the density. So capital K, X, C, rho. Okay? I will give a name of this. Then this is the logarithm, gradient of logarithm of this capital K, X, C, rho square. Then minus rho times this B, X, C, and I write it in the upstairs coordinates. So in this way, this is this. Okay, so it's this one. We can check this for the harmonic case. I mean, for instance, when rho equals to 0, so then here it's symmetric, so it's like in the random case, you can replace this by Martin kernel. So you do the same computation, it should be Laplacian plus rho x applied to this guy. Right? So then what is the Laplacian? So the second term should be, let me see, okay. So the point is that actually the, what's that? X, so you have two terms. One is Laplacian S applied to this you have minus here. You have minus, and so you have a logarithm of k. Kx c 0. This is one term. And the second term is minus x. Here you have rho. And what is this one? This is a gradient of logarithm of kx c 0. Okay? So then when you take the integral, actually, the limit you're using ergodic theory will be the integral with respect to m rho. So actually this term, you have this gradient of log k. So then this minus this guy is just this one. Okay? And this term, you use gradient, Laplacian, then log. You remember this k is k will satisfy Laplacian where equals to 0. So finally, you see that when rho equals to 0, it's just this formula without this term. That's a classical one, okay? So then what we can do, you still remember you have the Ghosh inequality. I think I'm correct, or maybe not. So here is H rho will be less or equals to L rho times the volume entropy. So you always have this. It's also the same in this diffusion case. Should be similar proof, exercise. And we can actually move a little bit forward using these two formulas. Start from these two formulas, and what you can get, okay? Actually, it's another theorem. It's very cute, we think. It's after Vadim. He's not here, okay. Okay. So what is that? And S. So it's some result in a paper this year, not yet ready, okay? So what's that? Actually, you can see for any rho smaller than V, you will have the integral of this B, m rho, is always less or equal to V. The first thing we claim, and we want to say with equality only when the space Mg is locally symmetric. Okay? So proof. Five minutes, okay? So what's the proof? I want you to look at this, as what I said, this part, without this row, this guy, the integral, will equals to the integral of Boltzmann function. Or not Boltzmann function, there is a Laplacian of Boltzmann function. This B, the m rho will equal to minus, because it's a divergence of, in the x direction, in this diffusion case, divergence means you have this. It's not small, it's not this k, it's the density, capital K. So, okay, so this guy will equals to minus x gradient logarithm of k x c rho dm. Okay? So now we use Schwarz inequality. This square will equals to the square of this integral, which is less or equal to what? Actually, we use this inequality twice. because this x is of norm 1. Then you get what? Then you get this integral, which is less or equal to the gradient of logarithm over k x c rho square dm rho. Okay? So that means I want to copy this here. So we have in a smaller size. We have the capital K x c rho square dm rho, then minus this one b dm rho square. Okay? So you see, what's the difference? We have two formulas here, and you see this is exactly h rho. You have this quantity, right? And I want to minus rho. Then I plus L rho times V, and there's another term here. So what is this? Is this V minus V dm rho? Right? Minus plus. And L rho times this integral. L rho times this integral is just this square. Did I miss something? No? Okay. So L rho is here. You have minus rho. Then you have minus rho there, right? And also you will have this integral square. So that's exactly this side. Okay? Now we can do the real proof. So what is the proof? You look at this. First, this is non-negative. This is greater equals to 0. That's what we Schwarz equality, right? And this is Ghosh. So this is less or equal to 0. Okay? You have some positive non-negative quantity, so this guy has to be, has to be none. Okay? But this arrow in this negative curvature case is positive. This. Okay? This is positive, so actually this guy has to be, you will have this inequality. So once you have the equality, you see what happens. You have very strong Schwarz inequality here. You use it twice. So then, once you have the equality, actually what happened is that not only this guy will be in the same direction of x, but also you have some ratio which is independent of points. Okay? So what does that mean? I mean, when this one hurts, if and only if this gradient of logarithm of capital K x rho, this one will equals to some constant function depend on rho, then times x bar. Okay? So then you start from this. Actually, you already see that, you haven't seen that. We still need some computations, but then if you start from this, I think the space is really very symmetric because the diffusion, your gradient is in the same direction of a geodesic flow. Okay? So actually, you can show this B is constant. So you can check that for the case when rho equals to 0 to see what happened. So if here capital K is just the Martin-Kernel for Brownian motion, so then this guy equals to this, you take the divergence. You take the divergence is this guy, as we see is the gradient of log K norm square, right? But this guy, we are in the same direction of x, and also it has a coefficient of tau, some constant, so it's a constant. So this means I try to convince you that we don't need computations to move forward, right? That's exactly the time for daydreaming. Okay, so now we move forward. So what we want to do okay, so you already see this M rho, this class of measure. When rho equals to V, you will have the Berger-Roebling measure, okay? And when this rho equals to 0, it's harmonic measure of prime motion. So we mentioned several classes of important measures in this class. There's one guy is missing so far. We mentioned once and didn't appear, is the Liouville measure. Actually. So we want to ask, what's the position of Liouville measure in this one parameter of harmonic measure? Okay? So question? So question is about where is the harmonic measure? Where is the Liouville measure? Okay? So a short answer. Is you try to see this by guess. By guess is if you are harmonic for this one plus rho x bar, then as this rho goes to minus infinity, it's the same as you consider this one. This operator. So when rho goes to infinity, the random thing will disappear, so it's invariant with respect to the inverse map of the geodesic flow. So some wide guess is that the limit might be the Liouville measure. But it's just wide guess, you don't know how to prove this, so a long answer. How we solve this problem, how we show if it's true or not. So it's long because it depends on how much time you want to spend in daydreaming by dynamics. So this means actually, besides this obvious dynamics, here I need to put a remark here because this theorem, the zero rho, that's what I mentioned, rho equals to 0 case is, here's a reference, is due to Vadim. Kaimanovich. I think it's 86, maybe, so that's me that don't claim this. Okay, so what do I mean by dynamics? Actually, there's other dynamics associated with this diffusion. Besides this natural dynamics, from probability point of view, we also have these dynamics from real dynamics, random dynamics. So what do I mean? So I mean we can define kind of random work in the space of diffeomorphisms or homeomorphisms which preserve the leaf. What do I mean? So further dynamics. I should not say further. It's like this. We need to introduce notations. What is the notation? First, we need to promote us to the orthonormal frame bundle. Okay? So what is this OM tutor? This is, for each point, you have some friend associated with this X, the space of friends. And this mu x equals to x1 nu 1 ud. We are in d-dimensional case, so this is of a normal frames in, let me erase this. Okay, it's in this space. This is at x. So let me put the name here so you of normal frame bundles of and tutor G tutor. Okay? So we will go to the frame bundle space. It's upstairs, even yeah, this is the orthogonal of a normal frames, okay? And now, since every leaf, what should I say? We want to introduce the frames of a normal frames in the tangent space to WS tutor. Right. This is WS tutor of this this point, any point here, x c, right? Okay. So we want to have frames tangent to this space. Okay. So since this can be identified so the of a normal frames can be identified with this O and tutor times c. Okay, no problem. So this is OS. Let me put the notation here. OSM tutor is, we just identified this with OM tutor times c. Orthogonal frames, of a normal frame bundle, let me put some name, OFB. Okay. So of B of in TWS. Okay? So all these objects will go downstairs, can be put downstairs because that's the place we use use ergodic things. So you will have the orthogonal of a normal frame bundles. This is defined as OS SM tutor quotient of gamma. Also, is the OFB in TWS. Okay? And, okay, now I want to say that for this space, for frames in this space, actually when you do the dynamic for these frames, you have to go to the tangent space, right? And you can define this kind of horizontal lift, this kind of metric thing, so I won't mention it here. So we can define for T, U, O, S, S, M, tutor, okay? So you can define, for this you can define the horizontal space and horizontal and the vertical space. So the horizontal actually means you have the covariant derivative with respect to this new UR0, right? This tangent. Okay? So similarly, you can define the vertical space. I won't mention this because this is not important. Okay? So far. And now what's the space? Actually, we want to consider this space, OS, SM tutor, is what? is the space of homomorphisms we are in some fancy space. Here, for any frame we use U, and here's a Cassy. X Cassy is for this leaf, we define the frames. And you have some homomorphism of this space, OS as M tutor. D is not a differential. I mean, it's just. Okay. This means I will explain now. It's a kind of we're considering the homomorphisms of this space, but we require this guy to be leafwise smooth. Leafwise smooth. So this is seeing this one. We are equal to phi Cassy x u. You apply to u, and you are still in this space. Okay. So where phi Cassy is C infinity diffeomorphism. Let me. Which depends continuously with respect to this Cassy, on this Cassy in the boundary. Okay. You are considered leafwise diffeomorphisms, and it's very so each time actually you are restricted to the leaf. You also you have your stable leaf, and on each leaf you have the orthogonal frames, right, tangent to this one, and then you consider piecewise, leafwise C infinity diffeomorphisms, but we require the whole map is homomorphism, and also this leafwise diffeomorphism will depend continuously in Cassy. Okay. So for this leafwise diffusion, we want to define leafwise objects. This is one step. This we don't need. Here we don't need. Because so you have a very natural question, maybe, is why we need to go upstairs to orthonormal frame bundles. Sometimes we even lost with the dimension of this space, right? So why go upstairs? And the reason is like this. So there's another natural point of view of dynamics related to diffusion is that you can have the equation for that. It's called the stochastic differential equation. Okay, so it's an analog to the flow case. Actually, in this random case, you also have flows, natural flows related to your diffusion. Then you can use flow point of view to interpret everything. Okay, so what is that? Let me make it by simply draw pictures, which might be nonsense, but explains what I want to say. Okay, so what is the Brownian motion in the on the manifold? Say, for example, here's the concrete disk, or is M tutor. So actually, this say for Brownian motion, actually you know how you construct Brownian motions on the manifold with a generated Laplacian on the manifold. The point is that you can consider this Brownian motion on the manifold as a transportation of the Brownian motion in the Euclidean space to your manifold. Then how you transfer it so that you maintain all the properties of the Brownian motion here is that, you see, for example, you have so you want something here very similar to your curve here, and with this change of direction similar. So what I do, actually the method is like this. So you start with some point and you pick up a frame bundle, of a normal frame bundle. So then locally you can look at this as a Euclidean space. Then you just move along, and here you have a curve here, say, then you move your of a normal frame bundle parallelly along this curve, and then you decide what to do next, because here you have this. So then actually you have a whole series of Stochanovich stochastic differential equation theorem to explain what I mean. So actually in this case, how you obtain the Brownian motion on the manifold, actually you obtain something in the orthogonal frame, orthonormal frame bundle space, okay? So what's the equation for this process? Is that this d nu t will satisfy this equation. In our case, you have this x hat. X hat, we will leave this geodesic spray to the horizontal space of this tangent of TOSSM, okay? You have the horizontal lift upstairs. And you have this, this corresponds to the drift turn of this diffusion, and then you need to plus the Laplacian part, which corresponds to upstairs. Here you have the horizontal lift of each, your friend, you have U1, U2. Say here, you have D directions. For each one, you can have the lift of your friends to the tangent space with this horizontal vector, okay? So that's the construction of this one, and here you have dBti, okay? So you need some time to understand this, but that's not important because we won't talk about SD here. So the picture is that what I said, how you obtain this promotion here actually is a kind of transportation. So now actually you have a very natural flow corresponds to this diffusion, is that if you start with different friends with different initial point, you let this go with time t, actually you will obtain a flow in the space of orthogonal frames. So that is called a kind of stochastic flow, okay? So that's why we have to go upstairs. This is one thing, and then I will explain. Stochastic flow corresponds to this process. This is not that simple as what I read here. Looks like a differential equation, then you have the flow, okay? So in the stochastic case, actually, it's a deep theorem there. You need to do lots of work to ensure you have this kind of flow, okay? Because it's in the random case. So, okay, I put some notations here. So, how many minutes left? Good. So I put some notation here. We will have some flow, time t flow of this flow, which equals to, each one is phi t rho, and because we are always on this leaf, right? So actually this flow is on this space. That's what I said, is leaf-wise it's kind of smooth. Because we are in the smooth case, we assume everything to be smooth, yeah? And So you have kind of flow so that with the law of this omega, this space, the probability here, a space corresponds to this Brownian motion. Brownian motion. Okay, here you have Brownian motion. Okay, you lift it upstairs and you have the drifter. So this is a flow. That means the map you introduced in this space, you have this kind of cocycle property along time t, along the t direction. This map will be phi c t. Okay, here you type the shift map. I put sigma s here, and here you have this phi. Okay, t. Anyway, it doesn't matter now. I think we understand, right? This is the and also the second is we are on the universal, not universal. We're always here, right? And tutor using and tutor things. The other thing is that actually you consider the map induced from any element from the fundamental group. Actually, this map will induce the tangent. It will induce a map in the of a normal frames that is denoted by d beta. This will commute with this frame. Okay, so it doesn't matter. Okay, once you because it's isometry. Okay, you put so it's it commutes. Beta. And what is the third thing? The third thing maybe is an important thing we want to understand because we're interested in the dynamic behavior when we change this rho. Okay? So when you change this rho, there's also a theory from SDE, we can guarantee in this case, we are able to differentiate this with respect to rho, and the differential will also give you the tangent, the tangent map corresponds to this flow. If you differentiate that in lambda, it's also where it depends continuously in rho and also computable. Okay, you have fancy things response to that, but everything is under control. Okay, so the third point is this rho goes to. Can you see the blackboard? Or I move it here. So the third point is that we have control. So this rho goes to this flow map. K is continuous, and also the derivatives, and this, and also the derivatives. Right? Okay. Also the derivatives and any object we want will be continuous in rho, and you have SDEs corresponds to. Okay. So you know what is the object. Maybe most time you cannot compute it, but you see it. Okay. This is a point. And now you see, with this, actually, you define some stochastic flow downstairs. Why? Because this guy commutes with the beta. So this, again, now we go up, downstairs. Actually, so this defines a stochastic flow on the space of this, okay, OS, SM, with distribution. You have the distribution. For each omega, you obtain, for each omega, actually, you obtain some map here. So, So then, what's the distribution? It's just you up to time t, right? That determined by this probability downstairs, okay? Original omega. Here you have some law, okay? So then you have a flow in this space. You have a flow in this space with this distribution, kappa rho s, small kappa rho s. And again, this kappa rho s will satisfy what? A kind of Markov property. Because this really generates a flow. You can go to time t, and it's independent, and then you go to time s. So you have this, but that's not what I said. So actually, you have this rho t plus s, where equals to kappa rho t, and convolution with kappa rho s. Then you have a process. Okay. Kappa rho s is just the distribution of these orbits, right? For each orbit, you obtain some map, right? So that's a distribution up to time t. Okay, so you have this. Okay, and now with all these things we introduce, we almost finish the second part. So what is that? The proposition is like this. Okay? So for any rho less than v, and what should I say? Okay. So, and for all f, upstairs, not upstairs, continuous function of OS, SM to R. Now, this is our space, OS, SM. I even don't know what's the name of this. It's of a normal frame bundle space, right, of SM. Okay. So, for actually, you will see that for any function which is continuous, you will see your measure m rho. If we lift your m rho to upstairs, now we go to the normal frame bundles. So what we put there, and which is tangent to the leaves of SM, right? To the stable leaves. Okay, so we put this m rho bar to be so that this is downstairs. You have the new x rho, right? Okay, and this is the x rho, and then you have for each point you will have the volume in the orthonormal frames. You put this volume here. So basically nothing, it's just it's a probability that which will project to m rho and also have a uniform volume, just volume in the direction of a normal frames, right? And let me put it here, and we project to this, and also we've normalized the big measure on the fibers. So that's what I put here. Okay, so if you define this measure just very similar to this M row, then you go upstairs, you see for any f like this, and you consider the integral of this f nu dm rho bar nu, the integral of this one. So what is this? What I want to say is that this m rho bar is stationary with respect to this probability. Okay, it's stationary with this one. So actually, here you will have d infinity. Here you have OS SM, and here you have OS SM. So here you have F phi U, you flow map phi to this, and D kappa tau rho T. Anytime T, it's inverted. It's stationary with respect to this. Okay? So this ends the probability part. So we want to go to this space of homomorphisms of normal frame bundles of asymptotic. Okay, we want to go there. Okay, and now still this is not our object. So what is our object? Because not only when we want to consider the random walk in this space, we not only need the transition probability, we also need the action. What is the action now? Is that now we consider the screw product. Map. So maybe safe to leave it for 1 minute of this thing. And actually the space we want to consider, because I'm short of notations, I just put something here. Okay, so this is G, and here you have the infinity and OS SM, and the infinity product, right? But I also want to include the deterministic case. I put 0 here. So times what? Because these are different homomorphisms on each leaf. So we want to apply this to act on this space. This is OSSM. Okay. So this is the space we want to consider the dynamics. So what is the dynamics? Now we have this shift of an element is this, now you have infinite many homomorphisms satisfying this property, and so you have one sequence. Now you have one sequence. You decide each time which map you apply, okay? So you have this sequence, and you have of a normal frame. And what's the map here? It's a screw product. Is that you have a shift here to it's a shift sequence. This is a sequence. Phi 0, maybe phi 1, blah, 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 blah. Okay. So you have the shift map, and here you apply the first element to your frame. Okay? So it's a kind of random walk in this space of homomorphisms, which is leafwise C infinity. So once we have this, and we want to put this big kappa. Let me put bigger kappa. I just don't want to add more notation here. This is kappa T. So actually, we can consider this for some time t fixed to consider this iteration. Basically, you can consider this t equals to 1. T1. So I put t here, this notation. This is just the product. Okay. So this is kappa, small kappa, a rho t, and you have the product. And you have m rho bar. Okay. So now, once you are in this random setting, actually you can consider the relative entropy, this dynamic system. So what you will get. So the picture is like this. Here you have the for normal frame bundle of all Sm, right? And here you have your random probabilities, right? You have some distribution here, which corresponds to this kappa, rho, t. So each time you have a frame here, you choose your homomorphism to apply to see what it will go, right? Okay. So then the relative entropy you define here is like this, kappa rho t. Okay. Epsilon outside of the entropy. That's P equals to minus, no, minus, okay. It's 1 minus, minus 1 over m of logarithm of m rho bar of the Bowen balls in this setting. Okay, so I can erase 1 for 5 minutes. Okay, so this is the Bowen ball. Yeah. Bowen balls associated to this dynamic system. Okay, so actually is you have your sequence of homomorphisms to apply, and you see here, should I put X or maybe nu, right? Yeah, it's U, it's better. U, epsilon, and N. Right? In this space, you have a distance. You can see this. And here you have the big kappa. Right? Okay, so then what's the conclusion? Actually, we can get is that in this case, it's very similar to the entropy formulas we get from the second class, but it's not related in equality direction, it's the other direction. That's S and it's 80. Okay, that's here. And actually we'll get this guy. So let me put time t, t equals to 1 for safety. I always consider that. The point is that when you consider this relative entropy, this random version of relative entropy, actually you will have this guy is always bigger or equal to the integral of the logarithm of the determinant of this tangent map over this phi. Restrict yourself to the direction of O, S, M. Okay. here is OS. I don't remember. It's OSM tutor. Should be like this. Okay. So you restrict to this direction. You have this tangent. Actually, then the logarithm of this one, you take the integral with respect to this kappa rho t, apply to this phi, and you have dm rho applied to your friend. Okay, so you have a lower bound. And it's the logarithm of this Jacobian. Kappa rho 1. Yeah, okay, thank you. Kappa rho 1. Okay. So what's the significance of this inequality? Actually, you know that once you have this lower bound, actually the Liouville measure, I'm not saying in this case, Liouville measure by this, let me see. Actually, Liouville measure, the Liouville measure will be characterized as the entropy will equals to the logarithm of the Jacobian restrict to the unstable direction, right? But here we're almost in that sense because, as I said, you have this minus 1 over rho of Laplacian s, then minus x. So actually, this stable leaves, if we have this rho big enough, it's almost okay, this flow is almost related to the negative of this geodesic flow. So this direction is exactly the expanding direction for this flow. Okay, so you almost have this. So you can guess what we will do next. Is to derive from this a kind of rigidity in some sense. Okay. But I want to mention that this inequality, you also need some, it's not that obvious. Because you don't have control of those densities of kappa k, not kappa k, the k, big capital K. So what we will use here, okay, I'm running over time. And so here, the proof of this one, we're using Manet. Hopefully this way, result. And also I want to mention that it's for the non-uniform diffeomorphism case, but I also want to say that in this case, this is endomorphism case. It's non-invertible case. So you have to change that. You can't apply this version. You need some thinking from endomorphism case. So this is my colleague, and here is the guy who is here. And so we have techniques to have these folding things, and then with that idea, actually you can show this the right direction. Okay. And now that this rho goes to infinity, and you still need to show other things, is the up semi-continuity of this entropy. If you have a limit measure, m rho minus infinity, you want to show you have up semi-continuity so that this guy has entropy with this one, the lower bound. And also you need some control when this diffusion goes to, you have to really kill this part, right? This is a random part. Of course, it's more or less there. As rho goes to minus infinity, this one will disappear, okay? So you still need some work. So with that, actually, we can have this theorem, which is here, and S again, it's a mispaper. So is that actually you will have this m rho as this rho goes to minus infinity, where converges weak star, where downstairs actually where converges to this m Liouville measure as this rho goes to minus infinity. So as a consequence, I want to put it here is that as a corollary, that's the quantity we want to study, is that when this rho goes to minus infinity, actually the integral of this b and rho will also converges to the integral with respect to Liouville measure, which is just the entropy of Liouville measure. Okay? So I end at this point. Thanks.